So today we'll be exploring the derivative of an exponential function, but first we should recap what an exponential function looks like and the restrictions on the base. So the base, b in this case, must be positive and it cannot equal to 1. If it was equal to 1, then you'd have a flat line. If the base was greater than 1, then your graph would be increasing, a curvy increase with a horizontal asymptote there. Or if it's between 0 and 1, it would decrease with a horizontal asymptote at the end of behaviors. Now, if we're going to graph the derivative of each of these functions, I'll use red. As you can see, the entire function is increasing, therefore the slope is positive, meaning the derivative function is going to be somewhere above the x-axis. In this case, it starts off as really not as steep, almost close to the slope is 0, and then it increases in its slope. So that means that the graph, the derivative or the slope, starts off very, very close to the x-axis and then it increases. So it has somewhat of a exponential function feature. Now over here, the graph here is decreasing, the slope is always negative, therefore your entire derivative function should be somewhere down here. Now you can see that the slope here starts off very, very steep or very, very negative. So we start over here. And as you look at the end behaviors, it's sort of flat, meaning the end behaviors, the slope is getting close to 0. So in this case, the graph may look like this, give or take. Okay. So, but these sketches are just rough sketches of the derivative. So let's call this one here y prime, the derivative. So the goal for today in the next slide is, how do we figure out the derivative of bx, derivative function? What is it from an algebraic point of view? So we're going to derive the derivative of b to the x using first principles. So this is our first step using the exponential function. And we're going to, from this step to next step, you're going to decompose using exponent laws from here to here. And if you notice these two terms, I'll call it, they both have bx. So from here to here, we're going to factor the b to the x. And if you notice, the limit is only affected by the h variable. And if you notice, b to the x is not affected by the h, so we're going to use properties of limits and let's just call it move it outside the limits. And we end up with this. All right, so from here to here, we're just going to switch them around from left to right. So in other words, the derivative of b to x is actually this piece. So in other words, the derivative itself is actually an exponential function. So now we're going to actually do a specific example and find the derivative of 2 to the x where the base is a 2. So in the previous slide, this is what we got at the end. So let's actually replace b with 2 to the x over 2 to the x. So now we have something, this limit here. And now anytime we see a b, we replace it with a 2 and h. So this is going to be some sort of number, which we'll figure out later. And then here we have the exponential part of the derivative function, 2 to the x. Now to get this piece here, at the moment, we're going to actually let h be really, really small, close to 0.001 or negative 0.001 and sub it in. And if you do that on your calculator, you're going to get 0.693 times 2 to the x. So this is your derivative of 2 to the x. So if I were to graph the derivative on this graph here, you can see that this piece, I will call this a sort of a vertical compression. So the derivative function is going to start off flat, but we know that the y-intercept is going to be 0.693 somewhere over here, give or take. So this black line here is the derivative function. It's a little bit vertically compressed. So like the other example, we're going to let the base, should be b, be equal to 3. So we do the exact same thing. So derivative of 3 to the x over dx is equals to this massive limit thing, 3 to the x. So we know that the function is exponential, but this number in front of here, which we'll figure out, so you actually do this, and you substitute a small number, h is very, very close to 0, into your calculator, and you end up getting 1.0986 times 3 to the x. So this here is because it's greater than 1, it is 3 to the x, but it is vertically stretched. So what that means is that the graph here, the derivative graph, is going to be a little bit higher than the original function. So recapping the two examples that we did, the derivative of 2 to the x is 2 to the x, but there was a vertically compression factor in front. 3 to the x, we just figured out was 3 to the x, but there was a slight vertical stretch. So right now we're going to be using Desmos. I'm going to show you graphically what it looks like, and we're going to actually change the base between 2 to 3 and have a look at the derivative function itself. So over here, we're in Desmos right now. So the red graph here is over here. The red graph is the actual function, and the blue graph is the derivative function. Right now, h, as you can see, is set really, really close to 0. Really close. And Desmos can't handle 0, but let's just put it here. Here. Okay. In this case, the base right now is 2, and as you can see here, when the base is 2, there is a slight compression factor. You can see the blue graph being a little bit lower, but when it goes to 3, and as I move from 2 to 3, let's have a look at what happens to the red and the blue graph. It seems like if I keep on going, as I increase the b value slightly, the derivative graph and the original graph are getting very, very close to each other. And up to this point, give or take, it seems like at this point somewhere, when the base is 2.69, the function and the derivative function are the same. So from the Desmos demonstration, when the base is 2.69 to the power of x, the derivative is also 2.69 to the power of x because the two functions overlap each other. Now, unlike 2 to the x and 3 to the x, there is no horizontal compression factor nor vertical stretch factor. In other words, the number in front here is 1. So we got the base for 2.7-ish or 2.6-ish from Desmos, but I'm going to show you how can you get 2.7-ish without using Desmos. So in this case, we have b to the x, and I want the derivative to be exactly the same as the original function. But in order for that to happen, this value in front has to equal to 1, meaning there should not be any compression factor or stretch factor. So I'm going to set the limit to equal to 1. I'm going to rewrite this out without using limits. And yes, I'm going to write this, that h has to be very, very close to 0. And I'm going to isolate for b because the whole point is to solve for b when h is very, very small, close to 0. So I'm going to bring the h over by multiplying both sides by h. The 1 is going to go over to the other side, plus 1 on both sides. I'm going to isolate b by taking the inverse of this exponent, the power. So in this case, it's going to be bh plus 1 to the power of 1 over h. So now we're in a position to substitute a very small number into here. We can't sub in 0 into here or it's going to undefine. So you sub in 0.001, and when you do that, you're going to get a number that's very close to 2.618-ish. The more decimal places, the more accurate the number. This number here is a special constant. A popular constant would be pi is 3.14, lots of decimal numbers after that. This number is actually called the natural number. So 2.718, we call it e, the natural number. In other words, if you determine the derivative of 2.718 according to Desmos and what we just did, the derivative is actually 2.718x. But instead of like writing out all those decimal numbers, we replace 2.718 with e to the x. So e is a constant. It is 2.718, and that equals to e to the x. So let's actually do an example of finding a derivative with e to the x. So let's just say I had e to the x multiply with x squared. All right. So to find the derivative, we're going to have to use product rule. So product rule says to find the derivative, you're going to have to take the derivative of x squared times ex plus ex derivative and x squared. In other words, we use power rule, that becomes 2x. We leave the ex on its own. That's the first part. Now the next piece is to find the derivative of ex, which we know is it is itself, and you have here x squared. So we're going to actually involve composite functions involving exponential functions where the base is a e. So just let's recap chain rule. So chain rule is when you have a function within another function. I'll call this the inner function, the embedded function, and this is the outer function. The first thing you're going to do is take the derivative of the outer function, but leave the inside function as is. And then the second step is to take the derivative of the inner function. So in other words, if we use this, all right, using g as e of x, what this means is you want to find the derivative of e to the power of f of x. So that's what it looks like with the exponential function. To find the derivative, well, we know that the first thing we're going to do is find the derivative of the outer function, which is e to the x. So we know that the derivative e function is itself, so we're just going to write down the derivative of e of x because it is itself. However, we need to figure out this inner function, which is going to be, in this case, f prime. So let's do another example here, all right, an actual real example. So over here, we have exponential function, base e, with a linear function inside. So to find the derivative of this, we're going to have to deal with the outer functions, which is, it is itself, which is e to the power of 2x. But the next thing you're going to have to do is take the derivative of the linear, which is 2x using the power rule. That will give you 2. And preferably, I like the constant to be outside the e of 2x. Okay? In this particular case, we have a quadratic function inside the exponential function. The derivative of this is going to be bigger. The bigger picture is e to the 3x squared minus 4x, which is the outer function, but then we have to take the derivative of what's inside or embedded, which is in this case using the power rule, 6x minus 4. So in this example, I think it's a good time for you to pause the video so you can try these on your own, and after you unpause it, I will take up the solution. So the very first example, I think we actually did this already, so I'm not going to actually take this one up using the product rule. Over here, we have a bigger picture is a quotient rule. So going back, quotient rule, when the function is numerator denominator, you take n prime d minus d prime n over d squared, where n is the numerator function and d is the denominator function. In this case, we're going to take the derivative of, in this case, e to the x prime sine x minus sine x prime and then ex all over sine x to the power of 2. I don't have enough space, so I'm going to have to go over here. So if you do this, let's actually do each piece here. Well, e to the x derivative is it itself, sine x, minus, now going back to previous lessons, the derivative of sine x is going to be cos x, and then you have e to the x all over sine square x. Okay. This one here is very similar to what we did before. There is a quadratic, is a composite function, so the derivative of this is going to be itself multiplied by the derivative of the quadratic, 2x plus 3. Now this one over here, I'm going to have to move it over here. I'm running out of space. As you can see here, it is a composite function, but there's actually more than 2 functions involved. So the bigger picture is exponential, but if you notice this part here, there's actually a square root function, but inside the square root function, there is a cubic. So before we start this off, it's best that we rewrite the exponent part as a exponent to the 1/2. And then we can take the derivative. So let's deal with the bigger picture first, which is the exponential, which is itself. So I'm just going to copy exactly the same thing here to the power of 1/2. The next thing is, what's the next function? It is the square root function. So we're going to use chain rule. We bring down the half down. We maintain the cubic. And then we bring it down to drop it down by 1 degree. We don't need this piece here. Oops. And then after that, we take the derivative of the next function, which is the cubic, which is 3x squared plus 3.